Feeling like taking a coffee break? So do I. What about we talk about the Vector API, designed to leverage the SIMD capabilities of your CPU. This API is super interesting and could be used in the future to tremendously improve the performance of certain very common JDK features, like array comparisons or strings conversions from one car set to another. The Vector API is described in the JEP 438. It is available in the JDK 20 as an incubator API, so you can already play with it. What you also need to know about this API is that it uses very specific features of your CPU, that is, assembly instructions that may be there or not. This is a Java API, so everything is abstracted as Java code. But if the assembly instructions you actually need are not there, because your CPU is too old or not of the right type, then you will not get any performance improvements. So, as usual, when it comes to performances, measure, don't guess. The Vector API is about using the SIMD features that your CPU may have. So first, what does SIMD means and how does it work exactly? SIMD means single instruction, multiple data. It's not something new. In fact, this acronym has been created in the 60s. Back in the days, there were these super parallel computers made by Texas Instruments, Cray, or thinking machines. These machines were based on this architecture. Don't be too jealous because you probably have more computing power in your pocket as of now. So SIMD has to do with parallel computing. Wait, don't we already have parallel streams? Why would we need something else? To answer this question, we need to understand how parallel computing is working. So let us go back one step. How is your CPU working? Well, there is a bunch of so-called processing units in it that are actually conducting your operations. An operation can be a unary operation, like incrementing an integer, or a binary operation, like adding two integers. Note that, for some reason, adding two integers is actually not the same operation as adding two floating point numbers. In all cases, these operations need one or more operands and produce a result. This result is made available after a certain amount of time. In CPUs, the time is actually measured in cycles. An operation can take 0 cycles, because you have many optimizations in your CPU that can make simple results available no matter what. So if you need this result, well, you have it literally in no time. But usually they take at least 1 cycle, and sometimes much more than that for operations on floating point numbers, for instance. So in a nutshell, your operating unit is capable of computing one value at a time. This value is sometimes called the scalar value because it is just that, one value. And your program will ask for different operations to be executed in a certain order. Because you have several cores in your CPU and each core has several operating units, you can have a bunch of operations executed at the same time. And to handle that, you have this notion of thread. Each thread can execute a series of operations, one operation at a time. The series of operations executed by a given thread is different than the series executed by another thread. So each thread executes its own program. This program can happen to be the same than the program executed by another thread, but it is executed in a different way. And because you can have several threads running at the same time, each one on its own core, you're actually executing this operation in parallel. This is the first way of doing things in parallel. If you have some massive computation to conduct on a massive chunk of data, you can split this data into smaller chunks, distribute these chunks among several threads, and hopefully you will have your result faster. This is how parallel streams are working, and it works very well. This way of doing things relies on concurrent programming, and the problems you may have are the problems of concurrent programming: race conditions, visibility, inter-thread communication, all this good stuff. SIMD machines are not working like that. They rely on a totally different approach. SIMD computations do not use threads, which in a way can make your life much simpler. A SIMD machine uses many operating units, and all these operating units are actually executing the same operation at the same CPU cycle. That is, at the exact same time. What they share is the program being executed. So all these operation units see the same program and execute it in the same way. What they don't share is the data. They are all operating on different operands. Instead of loading some random integer value from the memory, a SIMD machine sees the memory as an array of values. If your operation is load this value in the operating unit register, it is not one value that is loaded, but actually a bunch of them, corresponding to the size of this array. And of course, limited by what your SIMD machine can do. And all this is happening on the same CPU cycle, thanks to the way the SIMD hardware is organized. Your SIMD machine sees the memory as an array, and each operating unit sees one particular cell of this array. If you execute increment, then the values loaded are incremented, all in the same CPU cycle. Why? Because once again, every operating unit is executing increment on the same CPU cycle, but on a different piece of data. It is usually described as a vector computation, because your operand is actually an array of components that you can model as a vector. Loading a vector, incrementing a vector, adding two vectors, all this makes sense with a SIMD machine. As you can see, this is a very powerful and efficient way of computing things in parallel. That works well as long as you can structure your data in arrays of numbers. With a SIMD machine, you can conduct your array-based computation in parallel very efficiently, because if you have 16 computation units, you can handle vectors of 16 components, and you will go 16 times faster. A SIMD machine allows you to conduct your array-based computation in parallel without relying on concurrent programming. For this to work, you need to have all this hardware architecture available in your CPU. And because things are not that simple, you also need to understand how things are really working and what your CPU can do. The first thing you need to decide is the type of number you are using. It can be byte, short, int, long for the integer types, and float or double for the floating point type. Second, this array stuff is actually called a vector in the API, and you will see in a minute how you can create a vector from an array and vice versa. And third, you have only a limited space to store a vector, which depends on your CPU. This can go from 64 bits to 512 bits as of now. So if you have a vector of int values and 256 bits to store it, your vector can have 8 components. Same for a vector of float numbers. This number of bits, which is defined by your hardware, is called the shape of a vector. The combination of a shape and the type of component you need, int, short, double, and the like, is called the species of a vector. And the vector API lets you know what is the preferred species of a vector, given its type, for your CPU. Let us see some code in action and let us create and play with our first vectors. Here is the sum of two arrays, as you may write in a very classical code. So now let us write it as some vector code. First, you need to create two vectors from the two arrays you have and an array to hold the result of this computation. You can create a new vector from an array just by calling the fromArray method, passing it your array. This method needs to know two things. First, the species of the vector you want to create, which is basically the shape of this vector. And second, the portion of the array you want to load. And this is the starting offset. In this example, we are using the preferred species of the int vector, and we load the whole array, so the offset is 0. Once this is done, adding the two vectors is just a matter of calling the add method, super simple, that creates a new vector with the result of the addition. Because all this is executed on a SIMD machine, this add operation adds all the components of these two vectors at once in the same CPU cycle. This method call is actually doing the addition of all the elements of your array in parallel. Once you are done with your vector computations, you probably want the result backed in another array. This is what this intoArray method is doing, that also takes an offset if you need it. So in the end, you have a very simple pattern of code that does your computation on the SIMD machine of your CPU, which can give you amazing performances. Unfortunately, this code works only if the size of your array matches the size of the vector your SIMD machine can handle. Remember that a vector has an overall size that is limited, and if this limit is 256 bits, this code can only work for arrays of 8 int values. So you need to handle that, and the complete code is a little more complex than this one. Suppose that the length of your array is bigger than 8. What you can still do to leverage this API is to slice it, take 8 int values at a time to create a vector, and add this vector. The problem is that this value 8 depends on your CPU. Suppose your vector has a shape of 128 or 512, then this 8 will in fact be a 4 or a 16. Fortunately, this species object has a length method that gives you exactly this number. The exact species you are using is only known at runtime, but you can query it. So the code becomes the following. You can loop over the elements of your arrays, jump from one block of element to the next one, depending on how many components your vectors can store. Then you need to create your vectors by selecting the right elements in your arrays, starting at the right offset, which here is just index. The API will take the right number of elements, matching the size of your vector. Good, you're almost done with this pattern, but not quite yet. Because you may be in a situation where your array has 22 elements, which is not divisible by 8. So in the last loop, you do not want to take 8 elements. In that case, you want to take only 6. Fortunately, the API is here again to help you. In each loop, you can ask for a mask, which is just a vector of Boolean values that tells you which values have been taken from your array. This mask has the same number of elements as your vectors. If a component of your mask is true, it means that the corresponding component of your vector has been taken from your array. Now the nice thing is that you do not need to handle that yourself. All the methods you can call can also take this mask as an argument and use it to conduct your computations correctly. So the previous code becomes the following. First, build a mask, and then pass it as an argument to all your vector methods. To get the final result in an array, you need to fill this array step by step, passing the mask, and the last elements of data will be handled properly. The complete pattern becomes a little more complex, but it's still super powerful. Now, unfortunately, there's a caveat there. This masking stuff works well, but not on all CPUs. Some SIMD machines do not support this masked vectors feature. So if you write your code using mask, but don't have this feature on your CPU, your code will be less performant. The right thing to do in that case is vectorize your computation when you can fill vectors completely, and for the remaining elements, use a classical loop. Fortunately, you have a method on a species object that can tell you how many elements you can move to create complete vector. The loop bound from your species object that takes the length of your array can determine how many elements you can take to have a fully filled vector. So in that loop, all these elements can safely be added to vectors. You can then process the remaining elements in a classical for loop. The performance of this mixed pattern with SIMD features and a classical for loop are usually better than using a masked vector when your CPU doesn't support this feature. Alright, so you saw how to add two vectors together, how to deal with the limitations of your hardware, and how the Vector API can help you in that. Before you see more operations on vector, let us clarify your point of vocabulary. So far, we talked about vector components, but it turns out that the API called these components lanes. So a vector lane is in fact a component of a vector. Why is it called a lane? To denote the fact that this is the way your data flows in the SIMD machine architecture. That being said, you will find two kinds of operations on vectors, called lane-wise operations and cross-lanes operations. Cross-lanes operations compute something from the different lanes, that is the different components of a vector, by mixing these components together. For instance, sorting the components of a vector is a cross-lane operation. Or reducing these components to compute a norm, for instance, or an average, or a sum, is also a cross-lane operation. On the other hand, a lane-wise operation only operates on one lane of a given vector at a time. It can combine this lane with another lane from another vector, for instance to add them, so adding two vectors is a lane-wise operation. Now let us play with these operations. Let us compute the norm of a vector. That's a very classical operation. All you need to do is sum the squares of the components of this vector and take the square root of the result. There are two steps in computing the norm. First, compute the square of each component, and then reduce the vector with a sum. The first operation is a multiplication. That's a lane-wise operation, and the second one is a reduction, thus a cross-lane operation. The beginning of the code is the same as previously. You can just create vectors from the array using a species and a mask in a loop. Then you need to multiply this vector by itself, component by component. And when it's done, you just sum the components. This is what this reduce lanes method is doing. It needs an operator that tells that what you want to do is a sum, and a mask to make sure that the sum only takes the right components of your vector. Remember that if your CPU does not support masking, you need to write this algorithm in another way. Once this is done, all you need to do is to take the square root of this sum to have the norm. But here again, you can do the reduction in two ways. You can do it one vector at a time, or accumulate the partial sums in another vector and then reduce this vector. This is what this second example is showing you, with a pattern that avoids the use of masks. In a first step, you can vectorize all the parts of your array that can be fully vectorized. And then, instead of reducing each one of these vectors, you can reduce each component in the vector v. And by the way, this vector is initialized with 0, thanks to these factory methods conveniently called 0. And if you need to fill a vector with some other value, you can call broadcast instead of 0 and pass this value as an argument. And then you have the remaining of the components that did not fit in vectors, and in that case, we process them in a classical loop to avoid the use of a mask. You can use a similar pattern to compute an average. In that case, you do not need to compute any square, so no multiplication, and at the end you need to divide the sum by the length of your original array. As you can see, the reduction operation is passed as a constant. You have several reduction operations available: add, of course, mult, min, max, and several Boolean and bitwise operations. You may be wondering why you cannot pass a lambda to define your reduction operation, like you do in a stream API, for instance. Well, in fact, all these operations are defined by your SIMD machine. They correspond to specific assembly instructions. This is why they have been exposed as constants in a vector API. Let us implement another useful pattern, a filter reduce. Suppose you have an array of int values and you need to compute the average of the values greater than a certain limit. So first you need to spot the right values you need in your vector. This is a lane-wise operation that you can invoke with the compare method. So the beginning of the code is the same. You loop over the elements of your array and transfer them to a vector chunk by chunk. Here we are using a mask to handle the last chunk properly. Once again, you can also do that differently. Then you call the compare method on this vector, passing the greater than operator. All the comparisons you can think of are available, including comparisons of unsigned integer. And once again, these operations are defined by your SIMD machine as assembly instructions. This is the reason why you pass a constant and not a lambda expression. Now, this compare call returns another mask telling you which components of this vector passed the test. And no, this time there is no way you can avoid the use of this mask. So if what you want to do is just a filtering and get the result in an array, what you need to do is compress your vector. This compress operation is a cross-lane operation that removes the component for which the mask is false. It produces another vector, usually with less components than the original vector. So now all you need to do is copy this compressed vector to your array at a position that you need to increment in each loop. And for that, once again, you have a nifty method on your mask that tells you how many true values it contains. That's the number of elements you have added to your result array. If what you need to do is to reduce your filtered vector, then it would be a waste of time to create this array. What you can do is just reduce your vector using the mask you built with the filtering, accumulate this reduction in a variable, and count the number of components you reduced from the mask with this trueCount method. As you can see, the operations you can conduct with this API are very low level. You are operating on arrays of numbers, and you really need to design your computations as a vector computations rather than a scalar computations. Most of the time, the only loop you are going to execute is this outer loop that copies your array in a vector chunk by chunk. Then you have your computation that is conducted in parallel over the components of your vector, and that's it. Hopefully, you should get much better performances than a classical loop-based or stream-based approach. How is this API doing performance-wise? Well, it really depends on what you are doing and on the hardware you are running on. The good news is that there are actually many places where the JDK itself can leverage this API to improve some computations. If you want to see benchmarks as well as patterns, by the way, you can check the page linked in the description, which is a JDK page where you have very interesting examples. I will just give you one example, which is the equals ignore case benchmark. It just compares two strings of characters of various lengths, ignoring the case. These are the performances measured on my machine with the current JDK implementation based on classical loops, and second with a vector implementation. As you can see, past a certain size, which is rather small in fact, the performance gain is tremendous. There are other examples on this page that you can check, and that shows that very common operations can benefit from these performance gains, like array comparison or string conversion from one card set to the other. And there are many other less visible places where the work done for this API will also improve the performances of your application. The C2 just-in-time compiler can actually use this SIMD machine without the need for you to change your code. Free performances, I love it. And when this API is made final, you will be able to leverage it to improve the performances of your applications. And with this, I'm out of coffee. So that's it for today. Talk to you soon.